Hello, good morning everyone, and welcome to the morning session of the conferences. This morning we have the pleasure to have a plethora of participants, very interested participants, and also the theme resonates a lot with the current Anthropocene collapse that we are kind of experiencing in terms of climate change. So the session title is Mediation and Environment, and we have an astro scientist that is doing a wonderful work on turbulence and aerodynamics, Felipe Portela. Also, Rosemary Lee will talk about her own practice in the co-option of scientific imaging techniques and correlate that towards artistic practices to contribute to new forms of visual knowledge formation. Jamie Pereira will talk about his response to the Anthropocene climate collapse we're all experiencing in terms of submerging people in deep listening environments. And then we have a roundtable with Martin House and Ivo Louro, where they will talk about a new theory of becoming geological and questioning rendering experimental environmental change and exchange through the anthropogenic. So I feel these are themes that resonate a lot with what we're all experiencing, and I hope we have a very nice discussion afterwards. Okay, thank you. And let's welcome, please, Felipe Portela. I don't know if he's...
Yeah. Hello.
Okay.
Let me share my screen. Okay, what is this? So can I start?
Yes.
Right, so first of all, I wanted to thank the organization for the invitation. I confess it's the first time I give a talk outside of my comfort zone, which is around people who do fluids in general. And so I'm not sure if the format allows, but despite the Q&A at the end, if you wish to interrupt during any point, please feel free to do so. And so I currently work as a fluid dynamicist at the Lille Fluid Mechanics Laboratory, which is in northern France. But I'm an aerospace engineering by training, and I just became fascinated by the problem of turbulent flows. And I show here in this first slide a picture of one of the flows that I'm studying at the moment. So a brief overview of the talk I'll give today, and start with some definitions. So what exactly is fluid turbulence? It's not so simple to give an exact definition. So fluids are any material that can deform under action of an external force. So if you think of a solid and you push it, the shape of the solid won't really be deformed as you push it. But if you think of water or air or honey or any other thing that can flow, then it becomes deformed as you push it in a given direction. And I have here three examples of turbulent flows in nature. On the left, we have a plume, which is formed by a volcanic eruption. And you can imagine that as a volcano ejects material into the air, it pushes the air out of the way, and the motion of the air itself starts to carry these particles all over the place, and essentially interacts with the wind around it and so on, and forms these I don't know if you can see my mouse, but it forms these beautiful structures, these very large sort of structures that you can see in the flow, but you can also see a lot of detail which gives rise to this large structure. In the middle, I have a picture of phytoplankton blooming in the Baltic Sea, a satellite picture, and the brightest areas indicate large concentrations of phytoplankton, and you can actually trace the local currents of the sea just by looking at these contours. And it's a strikingly similar picture to the one on the right, which is of a satellite view of Jupiter, where the rotation of the planet gives rise to currents, and these currents give rise to these very chaotic motions with very similar behaviors to what we can see here on Earth. So, as I said, giving a definition of turbulence is quite complicated, but we can describe its properties, and the two main properties are its multiscale nature, which is something that you can illustrate with the concept of fractals in mathematics. And we have this figure here on the top left. So the concept that you have embedded in your problem a lot of different scales. So you have these very large swirls, but once you start zooming in, you see that you have smaller swirls and smaller swirls that seem to replicate the larger global structure of the problem. But it's also a chaotic problem. And what that means is that it's very, very hard to make long-term predictions, because any minor departure from, let's say, from your initial condition, or if you have some uncertainty in your data, once you try to make long-term predictions, a small deviation at the beginning will give rise to very, very different outcomes. And so the classic example we have for chaotic motions is that of a double pendulum. If you lift this pendulum and you let it swing, then you start to see that it just goes around in a so arbitrary chaotic motion. And if we combine these two top pictures and we look at the bottom figure on the bottom figure, which is showing ocean currents, we can see these two properties quite clearly. We see that these lines that I'm showing are basically the paths that the water is going through, the direction in which it is going. And they're extremely convoluted, they're very wrinkly, but they seem to have some underlying organization. And you even see some patches where things are swirling around in the same place. And so that would be the fractal property of this flow. But the chaotic property tells us that if you are sitting just slightly below from a given one of these lines, so if you follow a line, that would be the path that you would travel if you follow the fluid. If you sit just slightly behind, you may end up in a completely different place. All right, so that's it for a broad definition of the problem. And I have here some artistic depictions of turbulence, because it's been quite an attractive problem, not just for engineers and physicists. And Da Vinci's, these drawings by Da Vinci are probably one of the earliest depictions that we have of turbulent fluids. So here on the left, he was drawing a bar that he put inside water, and he tries to draw the motions of the water around that bar. And on the right, he's drawing how a jet of water falling into a pool, how that generates a whirlpool of wrinkly or of eddies of circulating motions. And I find quite interesting that there's also this drawing in the middle, which is not of turbulent fluids, but you can see that within the drawing itself, you can sort of see the same properties from the left and right. You see that the braids of the girl's hair provide some sort of structure. You have these sort of organized lines, which is where the hair is stemming from. But eventually, when you start to follow the individual pieces of hair, you see that they're a bit all over the place. So there's an underlying organization, even though everything is sort of messy. So other examples, quite classical examples, are the Starry Night by Van Gogh. And you can see again these swirly motions in the drawing. And you have here on the right this great wave of Kanagawa, and here you can see quite well depicted the idea of a fractal structure. So you have the breaking of this wave into these large patches, but each of these patches is replicated into smaller and smaller patches. So if you were to zoom into this picture, you would see a replication of the large scale picture. So I'll keep questions to a minimum, but it wasn't, even though we had these pictures from fluid flow from the 15th century onwards, it wasn't until the 19th century that we had the mathematical description of the motion of fluids. And these two guys, Claude Navier and Sir George Stokes, they came up with these equations which depict the simplest possible motion of fluids. So the top equation simply means conservation of mass. If you draw a box and you have fluid flowing through that box, then the top equation tells you that whatever goes in has to go out. And the bottom one is a more complicated version of Newton's laws of motion, but it simply tells you that if you apply a force to a fluid through this pressure gradient here, so you apply pressure on the fluid, it will resist with a force which is due to its own internal friction, and the resulting balance or imbalance will result in the acceleration of the flow, which is on the left. And the acceleration looks a bit weird. You have this term here, which is the complicated part of this equation because it's a so-called nonlinear term. And so once you start having small deviations in this guy here, this is the fluid velocity, this produces a plethora of different scales of motion. And for mathematicians, this is quite an interesting problem. They're actually offering $1 million for anyone that can show that it is even possible to solve these things by hand. So that's not really a problem that I'm concerned with because I'm an engineer, so I don't even understand the wording in this text. What we want to do is find ways to come up with models and make predictive statements about different turbulent flows. And so about a century later, after the writing of those equations, a guy called Osborne Reynolds came up, and he was interested in the problem of predicting how much pressure you need to push fluids through pipes. And he realized that you could scale the problem in terms of a characteristic velocity, a length scale, and the internal resistance of this fluid. And so what this number means is that if this number is very large, you'll get chaotic motions, as you have here on the top. And if it's very small, you have very organized motions in the fluid. And so the example on the left is rising smoke. You heat a bit of, so you can light a cigarette or something, you produce smoke. The heat is going to reduce the density of the air. It's going to start accelerating and moving up. And as it accelerates, it gains velocity. So this number here starts to increase. As it increases, it becomes extremely unstable and it becomes turbulent. Now, the interesting part of this is that it tells us that the same equations of fluids apply to any problem that you want, so long as you can rescale the problem in terms of this single number. And these two figures on the right illustrate this, in my view, quite well. We have here a cylinder which is immersed in water. And you see that you get these patterns developing downstream. So you're pushing fluid past a cylinder. And on the right, we have atmospheric flow past the Madeira Island off the coast of Africa. And perhaps if I zoom in a bit, you can see these swirly motions, which resemble very much these ones that you can produce in the laboratory. So we're able, through a single number, to rescale the problem down and reproduce it in the lab frame. Okay. So that's it for definitions. And where is turbulence involved? So I'll just go through some selected applications. It's actually quite a short summary of where you can find turbulence in engineering. But let's say that you want to design a wind farm. Not only do you need to be able to predict what the wind conditions are going to be at the given place of installation of your wind farm, you need to be able to design your blades in an efficient way, and you need to be able to know, once the wind passes through your wind turbine, how is the wind turbine going to change the wind such that the turbine downstream of it is not going to be severely affected in terms of efficiency. Similar issues appear when you design planes. So here you see that the airplane moved past a cloud, and this disruption of the motion of air, once the airplane moves past it, it creates a downdraft of air. And so that's actually the reason why when you're taking off at the airport, you can't just have airplanes taking off one after the other, because once the airplane takes off, it pulls the air down. And if you were to take off right after it, you would interact with the turbulence produced by the previous plane, and you would have a very bumpy flight. And on the right, I have another example in engineering, which is that of barnacles or fluid resistance. Essentially, for the shipping industry, it is quite expensive to clean your ship hull and your propellers. And what engineers are seeking are better models to understand how much does it cost to carry on sailing with barnacles on your hull, and what's the right point to clean it, because the cleaning has a cost. You have to stop your ship, you have to spend money to send someone underwater to clean it, or to take your ship out of the water. But of course, if you imagine a ship covered in all of these small animals, it's going to increase drastically the resistance, and then you have more fuel consumption. So that's the sort of trade-off that we're looking for. Other problems that we have are with both weather and climate forecast. So here on the left we have a picture of an extreme weather event over Europe, this sort of cyclone arriving. But also, as mentioned by the introduction, in terms of climate, which is a very current problem, we need to understand what our actions now are going, how our actions now are going to impact the long-term climate. And as I said before, because this is a chaotic problem, it's extremely hard to make such predictions. And so what we need are models that are able to, in a way, give us some confidence or restrict the range of uncertainty within our predictions. Here in the middle, I have an example of something called urban flows. And if you are planning a city, you don't want to have accumulation of pollutants within certain areas of the city. And on the right, there's something called the Great Pacific Rubbish Patch, or something like that, garbage patch, which is a result of the ocean currents accumulating all the rubbish that we are dumping in the sea. And so being able to model these ocean currents means that we are able to go and find these patches of rubbish and clean the oceans and prevent environmental catastrophes. There are many other examples, but as you can see, it's quite a broad range of applications, and the problems are really not comparable between each other, even though they all involve the same physical phenomena. And so the way we tackle this is by reducing the problem to a bunch of simple problems, which we call canonical flows. One such problem is that of a wake, which I already showed before an example. You immerse a body in a fluid, you force the fluid past it, and you study how the flow moves behind this body. Similar flows are those of jets, and you basically push a fluid into a quiescent environment, and you can measure the turbulence downstream of this flow. Another particularly exotic one are mixing layers, but I quite like this figure at the bottom, which happens when you have a fluid which is moving much faster than the one at the bottom. And if you think of a mountain as creating an obstruction in the motion of the atmosphere, then on one side you have the fast-flowing atmosphere, and on the other you have, well, stagnant air. And by going over the mountain, you essentially form these large structures, which you can replicate in the laboratory simply by pushing fluid over quiescent fluid. Another kind of canonical flows are wall-bounded flows, and that happens when you are pushing fluid next to a solid boundary. So you just have a wall, and you blow air, and you see what happens. And on the top we have a laboratory experiment. On the bottom we have a numerical simulation. This simulation is of a wing, and essentially by introducing this solid boundary, you are telling the flow to stop at the boundary because it cannot slip, and because of this condition you are forming turbulence, and that's yeah. And so perhaps the most exotic one, I'm not sure if I have time, yeah. The most exotic kind of flows is that of homogeneous isotropic turbulence. And it is quite hard to imagine what it is, but on the left we have an experiment, and what they have done is they create a grid, and they push flow through this grid, and each of these elements of the grid, they create their own chaotic motions, and all these motions interact, and they create something which appears to be homogeneous, so it doesn't really change so long as you're looking far enough downstream. It doesn't really change where you look. On the right, we have a visualization from numerical simulations where they essentially solve those equations in a similar setting to this one. How do we model these interactions in these different flows? So that's actually my active area of research, something called the turbulence cascade. And it was first introduced by a meteorologist called Louis Frey Richardson in 1922. And it's encapsulated in this very short poem, which is that big worlds have little worlds that feed on their velocity, and little worlds have lesser worlds, and so on to viscosity. And so what this small poem says is that you have these very large structures, these large eddies that we were looking at before. They break down into smaller counterparts and smaller counterparts until the action of viscosity, which is a fluid resistance, destroys this process. And this guy in the middle, called Andrei Kolmogorov, came up in 1941 and produced what is the most successful theory for the turbulence cascade, which formulates this broad picture mathematically and makes actually quite accurate predictions in terms of what the energy of these different swirls should be. Now, the problem is that in order to make this theory, he has to make a bunch of assumptions. We know for a fact that the assumptions are wrong because we can go and test them in the laboratory and with numerical simulations, but the predictions still hold. And so that's the dilemma that we are faced now in this field of research, is how can we arrive at the right conclusion with the wrong hypothesis? And how can we replace this hypothesis with a better one, which can account for the particularities of the flows? And so to obtain data to test our models, we do experiments in the laboratory. I have here two examples of wind tunnels. A small one here in the lab where I work, which is a boundary layer wind tunnel. So they push flow in the direction into the screen, and they measure what's going on. On the right, we have a wind tunnel at NASA, which is a full-scale wind tunnel. And you can imagine that these facilities are extremely expensive to run. They require a lot of manpower, a lot of care, a lot of maintenance. And the measurements are extremely complicated. So on the bottom left, I have one of the most popular tools to study turbulence, which is what's called a hot wire. And what they do is they go with this tool in the middle of the flow, and they measure for a long time, and they get a signal of how the flow is moving. They take this point and they move it a bit away, and they do the same thing. And out of these many signals that they collect, they try to create a picture which can represent the measurements that they made. And on the bottom right, I have actually a photo of a festival because I think it's easier to see what is going on. But what is done in the lab is to shoot lasers. You dump some particles in the air. You shoot lasers. You take photos, and you try to measure how fast these particles are moving. And as you can imagine, due to the very properties of the problem itself, these measurements are extremely intricate, complicated, we have extremely limited data from them anyway, because you can imagine if you're just measuring a point and you want to make a global picture of what is going on, that's quite limited view. If you are shooting a laser, then you don't know what is happening next to the laser, and so on. We also do numerical simulations. That's actually my expertise. And I quite like this drawing on the top right, which was proposed by Richardson. He suggested that you could split the globe into a bunch of squares, and you would have one person computing the weather for each of these squares, and there would be a guy in the middle controlling and assessing the global weather patterns. And that's exactly, so this was a drawing in 1922, we didn't have supercomputers, but that's exactly how we do simulations in supercomputers. We split the problem, as we see here, into many small cells. Each of these cells is given to a computer. The computer solves the equations in these cells, and then we reconstruct this, and we have a picture of the flow field. Now, what happens is that to do numerical simulations, you have to use physical models, because to resolve all the scales of motion, it's extremely expensive. To give you an idea of scale, the simulations I've been running at the moment, we run on 400 processors over about a month to collect statistics, and it's simply the flow past a bar. It's nothing as complex as a full aircraft. So simulations such as the one on the left require physical models. And as I said before, the physical models we have are far from perfect. So just a summary, my alarm already went off. So we're able to identify some symptoms of turbulence in fluids, but we don't really have an accurate description of what this turbulence is. We can measure these properties in the lab, but it's extremely convoluted and we have very limited data out of it. Computers have been a blessing, but also a curse, because we can never really solve the problem directly. We always need to use physical models, and we don't have accurate physical models. So with that, I finish with animation of the work I'm doing at the moment, which is a combination of the two of those canonical flows. I've immersed these two bars in a uniform fluid, and that produces a jet in the middle. You see it produces these small structures going into this flow, but the obstructions themselves produce these very large structures which are organizing the whole turbulence. And so my current work is try to understand how each of these small objects here are behaving in relation to each other and how they determine the evolution of the flow as a whole. So that's it. Thank you.
Thank you, Felipe, for a beautiful, mathematical, complex, and turbulent presentation. I think it certainly relates to a lot of what we are trying to build up here, and for sure it relates a lot to my own work.